So what is meant by technology scaling? So as in the course introduction also I told you, the device becomes smaller and smaller. What is the meaning of device becomes smaller and smaller? As I told you, normally CMOS devices are used in the manufacturing of the ICs because it is more compact, less power dissipation, and we are getting maximum swing from 0 to 5 voltage, and there are so many other advantages also. And because of that, we are using our CMOS circuits for the IC fabrication. So now, are you able to see this particular figures? So here it is mentioned that technology node. Node means, as I told you, NMOS transistor, PMOS transistor, and channel length also I had described. So as the length of channel decreases, device becomes smaller and smaller. So that is mentioned over here. So here you are able to see this particular graph where 0.35 micrometer is the length of the PMOS or NMOS, whatever the CMOS devices use. That is the channel length, which is shown by this particular technology node. Here it is 0.18 micrometer, means the length of the channel is 0.18 micrometer. Now just see over here. It is only 7 nanometer, means device is so shrinked or becomes so small. That's why you are getting so many smartphone, compact smartphone having so many facilities over there. So what is happening? Your device is shrinking down and the device is become more and more compact and power efficient, and although it is more complex, but functionality wise it is more functional. So same way over here you are able to see in 2003 the channel length was 90 nanometer, but now as it is going up in 2016 it is 16 nanometer. But every time you are not going to reduce it like that 1 nanometer ऐसे हो सकता है क्या? नहीं. Beyond that there will be another technologies available. You are doing in that way because some channel value is required over there, current to flow, device to work, threshold voltage should be there. So we can't go beyond certain limit, but here it is shown that this is 14 nanometer over here. Now here again there are two colors are mentioned, that is the yellow and pink. Yellow is mentioning core supply, means what type of voltage is required for the core to operate. Core means suppose I am having microcontroller where it is actually performing its task, that is control unit is there, ALU is there, and it is calculating the things. For that whatever voltage is required, that is for the core supply. So here 0.8 voltage is required for core to operate. Inside voltage means on which core is operating. And what is the outside voltage? That input and output we are getting IO. So that output voltage where we will be getting 1.2 over here. So that way the technology has been done over here. So here this yellow indicates core supply. For this case it is 0.8 and output supply is 1.2 volts. So there might be internally different voltage sources will be provided, driving circuits will be there. So for internal core operation it requires only 0.8 voltage, and for externally whenever you are taking output it will be providing 1.2 voltage. Hope the things are clear. So this technology enhances means your device is shrinking and it is becoming more faster. Okay, and density wise the device is circuit is become more denser. On the small chip of silicon, previously there are 10 transistor or 100 transistor, now it will be 1000, 10,000 lakhs of transistor you are having. So as the device is shrinking, the complexity increases and your device become more faster because routing delays will be reduced. But every time it is not possible that you will be getting some advantages over here. Some disadvantage might be there because if the device is shrinking, the current is not getting proper path to flow, and because of that traces which are having, that will be very thin and it will get wear out because of current flow. So power dissipation at some cases might be more, or in some cases might be less. So that merits and demerits we will be seeing over here. Hope the things are clear in your mind what is meant by scaling. Again, one example I am giving, that in mid-sem examination you are having 35 marks of exam, but 40 marks MCQ will be there, and it will be weighted to 20. Means we are doing scale down. 40 you are giving, 40 marks questions you are attempting, but it will be scaled down to what? 20. Likewise, you can consider the device is shrinking, so overall parameter will get shrink in that matter only, then that way only. Only I'm not changing length. All the parameters will be changing, that is the n plus region doping, or I can say width of the device, or other what are the parameters we are having, that will also get shrink. It is not only length of device is shrinking. Hope the things are clear. Any doubt in this, what is meant by technology scaling? Let me know in the chat box. I have given so many examples and so many proper options. What is meant by technology scaling? That is proportional. It is the change in geometric ratio. That is what we are keeping all the geometric ratios same. That is, if we are changing some length of the device, we will change the width of the device also. We will change oxide thickness also. We will be changing other parameters also. So it is not only change in the length of the device. Here, just we are changing the geometric ratio, parameter or any physical dimension in the proper ratio. Okay. So if I have scale down the values of one subject by parameter 2, so other subjects values also I need to scale down by 2 only. So it should not be variation in the scaling factor, which is over here is the S is what? Scaling factor. Here it is mentioned as a alpha, somewhere it is mentioned as alpha, somewhere it is mentioned as a S, but consider only one parameter, that is here we will be considering S. This is what I have taken direct picture, and that's why it is mentioned alpha over here. So it is like that. So proportional adjustment of the dimension of an electronic device while maintaining electrical properties of a device. Because although I'm changing the parameter, I'm scaling down different parameter, but device should work properly. Electrically it should be working as a MOSFET only. If its parameter or its VI characteristic or property is changing, there is no meaning for that. So while scaling, you need to take the consideration that whenever you are scaling down the device, your properties of the device should remain proper. It should get enhanced. It should not be get deteriorate. Okay. Now, as the device is becoming small, or you are doing the scale down of the device, the density wise, the device will become more denser. Means on the small area, suppose I'm considering this red area, previously there were only 1000 transistors. Now as the device shrinks down, there might be 1000 of more transistors in the small area. So your device become more compact, and density wise it will become more denser. So I can say it improves the circuit performance, because one device is over here, another is near to that, routing delays will be raised. Okay, that way your performance of the circuit improves. Okay, so this way you need to have a scaling. Why you require the scaling or technology enhancement or scaling down the device? It's mentioned over here. So moving further, so advantages of scaling. What are the advantages now? Just let me point out over here. High packaging density. Yes, because the device becomes small, so you are having more devices on the small area. Reduce the size of chip. Yes, as you are able to see in previous year, the small phones you are able to see which is having less functionality, but now in that much area you are getting full functional phone and smartphones. Okay, multifunctional chip will be adding more and more functionality in the same area or same chip. Improve current driving capability, improves the device characteristic. This way can comment afterward. Due to small geometric, the capacitance reduces. Yes, capacitance value will get reduced. Interconnection delays will be reduced. Multiple threshold voltage can be there, because if the device is shrink down, it will not be every time 0.7 threshold voltage. It can get reduced, and it will be operating on the smaller voltage or lesser voltage. That is the requirement. The device should consume less power, and that's why cost wise cheap it will be more cheap. Okay, so moving towards, this is as a theoretical part, I am not going in detail. You can read and you can relate, there is no problem. What is disadvantage? Now just tell me, just concentrate to this point. Suppose I am having this particular area. Okay, just I am drawing this particular area, and previously there was 10 transistor or 10 devices. Okay, now I am having same area, and as the device is shrink down and technology enhances, suppose I am having 100 transistors. Yes, you're able to see this. Now suppose here leakage current, power dissipation per device was 1 into 10. So that is 10. Power dissipation per device is 10, but here power dissipation per device is what? It is 100. So that wise dissipation per unit area increases, because in this much area there are more transistors, and as there are more transistors, so power dissipation per unit area increases. But power dissipation related to that device decreases because device becomes small, and that's why power dissipation per device decreases. So power dissipation what? Power dissipation per device decreases, but power dissipation per unit area increases because in this area there are more number of transistors, and if you are calculating all the transistors having power dissipation and that area, the power dissipation increases. Hope the things are understandable. Power dissipation per device, what? It decreases, but power dissipation per unit area increases. This is the first disadvantage we are having. Understood? Any problem in this? Because device becomes small, and that's why power dissipation per device decreases. But as such type of more number of devices are mounted on small area, previously there are only 10 transistors, but now there are 10,000 transistors, so power dissipation per unit area increases. This thing you need to understand. Hope the things are clear. Now here it reduces the carrier mobility because there are small area, and in small area there are thousands of transistors, so doping will be less, and as doping is less means carriers will be less, and carriers will be less means mobility is less, or we can say as the devices are more denser, it is having a bottleneck creating for the carrier to move, and that's why gain of the device decreases. Now due to reduction in the conductor size, current handling capacity of the device reduces. Previously the length of your wire is like this, so current can flow easily, but now as the device becomes shrinking, so it will become thin, and that's why if the current is more, it will get wear out or tear out, and that's why what will happen, the current handling capacity of that device decreases because the thickness of this wire is also reducing. Previously the wire is having more thickness, but now it is become more thin and thin, and that's why it will not be able to handle whatever current flowing, and device will become hot, and as device is becoming hot, we need to have a what, that is the additional facility for cooling. Heat sinks you need to use to cool the ICs, and that way again the cost will be there, burdening will be there. So there are certain advantages and certain disadvantages over here. So I have addressed these disadvantages properly. So moving towards the next point. Now, what are the different types of scaling? There are three different types of scaling. Out of that, two are very important. We are not addressing this that way. So there are two types. Now you are able to see everything looking like the same because it is a field over here, and here it is the voltage. But both are totally different. You need to remember this as a different and this as a different. And this is the lateral scaling. So there are three types of scaling. That is the constant field scaling. Second is the constant voltage scaling, and third is the lateral scaling. Lateral scaling is related to only changing the length of your channel. Okay, this we are not addressing. That is only gate shrinking is there, and it is normally not used. So here because the parameter is changing, although density wise it is more denser, but other parameter affect. That's why we are not addressing this particular point. This is just for the sake of giving that these are the 3 points. Now most important point is the full scaling and partial scaling. Now you need to relate it properly. Field scaling is called the full scaling. What? Field scaling is called the full scaling, where all the parameters of the device scale down by the same parameter. Meaning of that, if I am having W, I am having length. If I am having certain VGS, if I am having certain VDS, so every parameter will be. What is mean by partial scaling? Here all the parameters will not be scaled down. Only the W by L ratio or oxide thickness is changing, but the voltage will not be scaled. Voltage, if I am giving 5 volt, it will be 5 volt only. I am not going to change the voltage. So hope you idea is clear. So in full scaling or field scaling, all the parameters, that is voltage as well as oxide thickness as well as W by L ratio, everything will be scaled down by the parameter S, which is the technology scaling parameter, but rest of the parameter, that is the over here only W by L ratio, oxide thickness will be changed, but the voltage will be remain same. And that's why it is called as a constant voltage. We are not changing the voltage in this, but here all the parameter we are changing. Hope the things are clear. So just put the things in comment box. If we are having constant field scaling, if we are having constant field scaling, whether we are changing voltages also or not, yes or no, just put your comment. In constant field scaling, are we scaling VGS also, voltages also, yes or no? So Yash, Snehal, Supriya, Prajakta, yes. You have written answer as a yes. And Mayur, you have given wrong answer, no. So just no, it is related to previous. Okay, sorry. So everyone getting the thing, that is they are putting answer as a yes. Means here everything will be scaled. All the parameters will be scaled, but here all parameter other than voltages will be scaled down. But voltages we are keeping constant. So this is the basic difference is required to understand. Rest of the thing you will understand in the better way after this. Okay, so it is having now 2:55. I will be continuing for the 3 minutes again, and after that we will be launching second poll related to feedback. Okay, so the things are clear. Now you are able to see. Just we will go fast over here. So there are so many parameters related to transistors are written. That is the channel length is denoted by L, channel width is denoted by W, gate oxide thickness. You are able to see that oxide thickness SiO2. So that is the TOX. This is junction depth where we have just drawn like this. Just take me, let me take pen. And this is what is the N plus region, and over here at N plus region. So this XJ, this is the depth of junction. So this particular value from this to this is called as the junction depth. So this is denoted by XJ. Power supply voltage is denoted by VDD, threshold voltage VTO, and doping densities, that is how many impurities you are doping over there, it is denoted by ND. And this should be proper one, otherwise there will not be charge produced over there according to the Poisson's equation. So you need to provide this proper, otherwise there will not be charges and there will not be current flowing. So these are the different parameters we are scaled down. So in full scaling, we are scaling all the parameter by the same factor. So here it is scaled down by S, because this is my effective length L dash, and this is my actual length, which is scaled down by value S, which is the technology scaling factor. So after scaling down, this is my final value. Same way over here, this is my actual value, which is scaled down by parameter this, and that is my actual after scale down. This W is nothing but a W dash. So whatever the dash is mentioned here, it is by default not written over here. So consider it as a dash. So this is after technology scaling by S value, we are getting this. So actual value is this, and we have scaled down by value S, and that's why this is after scaling down I am getting this value. So in full scaling, what is happening? Every parameter is scaled down. So you're able to see every parameter is scaled down. But if you are scaled down this, we will not be having proper charge. And that's why you need to scale up this value. Okay. But here you are able to see constant voltage scaling. All other parameters we are scaling by value S, but voltage will be remaining constant. So we are not scaling down this particular voltage. Just see over here. It is VDD and VT. Without scaling, it is same, and with scaling, we are not changing the things, and that's why it is be same only. And doping concentration you need to provide properly, so it is increased by H square. So hope the things are clear. In constant field scaling, all the parameters considering WL, TOX and voltages, all parameters are scaled down, but here voltages are not scaled down. Rest of the parameters are scaled down. So this is the thing. And in next lecture, we will be continuing what is the effect of that scaling down of the parameter on the current density, linear currents values or other values in the coming lecture. So hope the things are